My talk is titled Hairless Apes Fall from Space, and it's about jumping from high altitudes. So, first off, we need to clarify what is space? Where is space? So, the International Aeronautic Federation defines it as being the Kármán line, so approximately 100 kilometers above the Earth's surface. That definition comes from, well, when you're flying, the higher you get, the thinner the air gets, and then the thinner the air gets, the faster you need to go to generate lift. And you reach a point where the orbital velocity is equivalent to the airspeed that you're going at, and there you're pretty much at space. Now, Kármán himself decided that the 100 kilometers was a nice round number and approximately correct, so that's what they stuck with. So anything above that, the FAI considers astronautics, space. Anything below that, aeronautics, air. So you can kind of see here, we have, actually, where's the laser on this thing? I don't really know, whatever. You kind of see here we have the different layers of the atmosphere. Now the stratosphere there where the plane is, that's the highest that we've jumped from. The Kármán line's a little bit higher. And then as you go higher, you actually get into real space. So, cop-out number one, we actually haven't jumped from space. As you can see here, all the jumps, as I mentioned, are in the stratospheric era. And then around that, a little bit below, you have where the SR-71 Blackbird flies. At the very top, you have Spaceship One, which was the very first private space flight. And you can kind of see that in the stratosphere, the pressure, the ambient pressure, is pretty much equivalent to what you would get at space. So, it's close enough. And now here's the important question. Why? Why did we jump? Well, back in the 50s and 60s with the advent of the space race, you kind of had the idea of, well, if something goes wrong, we need to bail out. So this goes with high-altitude planes or with spacecraft. So you had to figure out how feasible was it to bail out. And to do that, you required equipment development, equipment testing, so that involved designing parachute systems that would work in such conditions, and also pressure suits, so the crews of these vehicles wouldn't die from exposure if they were ejected from the craft. And then you need to realize, oh, what's actually going to happen when you're at these altitudes, if you do get a tiny bit of exposure? What's going to happen when you start going this fast, possibly if you end up cracking the sound barrier? So all these are things that need to be figured out, need to be considered. And for reason number two, it's cool, which falls into possibly marketing purposes, which would be Bull Stratos, which I'll be talking about later. And then cop-out number two, when you're talking about bailing out, you're going out of a plane. Well, any high-altitude jump from the stratosphere has been from a balloon because that's the easiest way to get a person up there and then out. It wouldn't really be feasible to have a spy plane go up to that altitude and then have the pilot eject and the plane go right down back to Earth in a horrible fiery mess. So, yes, stationary platforms. So, the very first step in this was Project Excelsior. Now, this was initiated after Operation High Dive in '58 by the Air Force. Now for High Dive, what that was you had the Air Force put a bunch of high altitude parachutes on dummies. And then they booted them from a very high altitude. These dummies ended up falling and entering a flat spin that reached 200 RPM, which is fatal to a human being and not really feasible if you're trying to get people down to the ground alive. So, they decided that they needed to go back to the drawing board, and they developed a new type of parachute that, when deployed, you would get a small drogue, a small drag chute, that even though the air is really thin, that would pick up enough air to stabilize the jumper and make sure that they don't enter a spin and die. And then when they reach a lower altitude, they can deploy their main chute and everything will be fine. And then also they need to consider, well, if we're up this high, these air crews need to be wearing pressure suits so that they don't die from exposure. So you had the Air Force also throwing on pressure suits as well. And then you have this guy, Joe Kittinger. He's now doubled his weight in equipment. He's now over 300 pounds. And then they throw him in a gondola that's underneath a 200-foot helium balloon that a bunch of Air Force techs have cooked up, and they let him fly. God, I love the 60s. So they did 3 jumps in total. First jump, they went from 76,000 feet. This was an unmitigated disaster. The drogue deployed early, it wrapped around his neck, he went into a spin, 120 RPM, he passed out, and the only reason he was alive at the end was because his chute deployed automatically at 10,000 feet. So not a great first step. What do? They go back at it 3 weeks later. This one went off without a hitch. He fell for 55,000 feet, parachute deployed, Joe's safe, it's great. Absolutely wonderful. So then they decided, what's next? Let's push the envelope. Let's crack 100,000 feet. Let's see where this goes. So they got him up there, and as he's going up, the pressure seal on his right glove fails. His right hand is exposed to the atmosphere. That's not good. He temporarily loses use of that hand. Now, most people are right-handed. Most parachute systems are designed to be deployed with your right hand. This is not good. What does Joe do? Well, he decides not to tell the ground crew because he was worried they might abort, and he goes on with it anyway, which, in my opinion, is not a great decision, but it worked out all right. He fell from 102,000 feet. He fell for 4.5 minutes and cracked 600 miles an hour. That's him leaving right there. And that's him on the ground. He's actually totally fine. It's just he's weighed down by all the gear, so they have to strip it off him. And actually, since this was before the age of GoPros, we don't have footage of his jump, except for the exit. They had cameras on the gondola. So if you can actually play this, we can see Joe jumping from 102,000 feet. And there he goes. What I really like from this other angle is that he really rolls on his back and he starts flailing. His technique wasn't great, but again, skydiving was in its infancy, so we'll count some slack. So now, what did this show? This showed that you actually can get someone down from that height, and you can get them down alive. Excellent. Proof of principle. So now, let's fast forward about 50 years. And now we have Bull Stratos. We've proven that we can get someone down, so this was more so about setting a mark. Now, Felix Baumgartner has a little bit of a background. He started jumping when he was 16. In his stint in the Austrian military, he joined their parachute demonstration team, and then afterwards, he ended up working for Red Bull doing demonstration jumps. And then he got bored. He felt he was a little bit too constrained with skydiving, so he started base jumping. And then he always was someone who wanted to push the envelope, so he decided to get a carbon jet-powered wing and fly across the English Channel. And then after doing that, he still figured, I can do something a little bit more. So he wanted to crack the sound barrier, and he sold this idea to the owner of Red Bull, Dietrich Mateschitz. And they decided to pursue that full steam. So they want to crack the sound barrier and also promote Red Bull. Because that's the way things work with Red Bull. So now, this is a civilian project. This isn't a government project. So you don't have the full weight and organization of the US military behind this. So they have to do everything from the ground up. They have to design a capsule that will actually be able to carry them up. They have to acquire the balloons. They have to acquire the pressure suit and helmet and design that, and the parachute system from scratch. This all has to be custom made. And they have to show these vendors who generally do government work and military work that these aren't just a bunch of yokels trying to do something cool. They're a bunch of smart people that are trying to do something cool. And the David Clark Company, which actually manufactures all the pressure suits for NASA and the US military, they had to be convinced. And for the very first time, they let a pressure suit get into the hands of a civilian for a civilian project. And then, because he's the only man that has jumped from this altitude, they had to bring on Joe Kittinger as a consultant. And then because they're setting a record, they have to get the United States Parachute Association involved because the records from exit altitude, for speed, those would all have to be observed and verified. And then they finally decided to go public with the project in 2010. They were then sued because someone felt they were stealing their idea. That lawsuit was settled. And then throughout all of this, Baumgartner was doing all this training in the suit. He was doing high-altitude skydives from 27,000 feet, trying to see how it flies. He was working with it in a wind tunnel to see the aerodynamics. He was doing bungee jumps to practice his technique for stepping off of the ledge of the capsule. He was hanging out in a pressure chamber as it got pumped down, just chilling in his suit. And they had to also test the capsule too. They had to put it into a pressure chamber. They had to put it through unmanned flights. You had to make sure that everything was working. Because with a promotional event like this, you don't want to have someone die. Now, we reached 2012. This is it. This is the final steps. And they felt, well, we're dropping something from the edge of space, or what we're calling the edge of space. We should do it in Roswell. So they did it in Roswell. And then they did 2 test flights. The first one, they went from 70,000 feet. At this point, Baumgartner has now been the only, he now joins the group of 3 people, well, he makes the 3rd, who have gone above the Armstrong limit, where if you're exposed to the ambient pressure, you will fall unconscious and likely die. Joe Kittinger was the other one, and then you had a Russian, Eugene Andreev. And that jump went perfectly. This image here is on the 2nd jump as he's exiting, and they did that on July 25th. And again, from a jump standpoint, that went pretty well. Unfortunately, the landing parachute for the capsule did not reinflate as it should have, and it smacked into the ground and was unsalvageable. So the company that designed this had to work around the clock for about 6 weeks in order to make sure that there was another capsule ready for the launch window for the final mission from mid-August to mid-October. But after an aborted attempt on August 9th, the final mission launched on August 12th. And 8 million people were watching live on YouTube. At 9:30 a.m., the balloon takes off without a hitch. It's perfect. And Felix climbs for 2.5 hours to 128,000 feet. And then this is what happens. At this point, when he opens this door, it's pretty much the same as if he was doing a spacewalk from the International Space Station. I absolutely love that view. Can we crank up the sound a little? That's not the sound. Had a nice beat though. I mean, no biggie. You can keep the video rolling if you want. So, or we can cut the beat. Thanks. So yeah, at this point, he's at 128,000 feet, and he's getting out on that step. Everything's good to go, and look at how huge that balloon is. There is a lot of helium in that thing. And that's a long way down. There's some really nice ambient music in this if we get to play, but yeah. Yeah. At this point, he's at the highest that anyone's really ever been if they didn't intend to jump. Some profound words. Slip the camera. And then he goes. Now, something really interesting to look at when it switches to his view. So he's jumping, and if anyone here has ever skydived or been in free fall, you have the wind that you're moving through that is pushing against you. Look at the stitching on the patches on his pants when you catch a glimpse in a second. They're not moving. at all. The air is incredibly thin up there. He likened it to in a post-jump press conference to, imagine you're swimming, but you can't actually feel the water. So he has no way to really right himself or to reorient himself. He just has to trust in his jump and his technique. And then, as we go a little farther, and you get a little further down, going a little faster, this is happening, which is not good, as I explained earlier. He's spinning. Yeah, he cracks the sound barrier, which is great, but he's in a really rough position right here. Now, he could deploy a drogue parachute, which was in his equipment, but he wanted to break his records, and that wouldn't validate them. And as he goes further and further, he starts spinning faster and faster, and then he finally gets his radio to work and says that he's been in a violent spin for quite some time. If you also look at his heart rate, it's doing funny things that probably were spooking people on the ground. But look, he's gotten down low enough. There's now wind. He can now actually grab something to, grab some purchase on the wind, on the air, to reorient himself. And at this point, he's stable. He's fine. Sure, he's at 55,000 feet, but at this point, it's a relatively normal skydive just from an extra high up place. And from here on out, everything went perfectly. Now this, I absolutely love every bit of this. This was an amazing project from beginning to end. You had a great, incredible engineering aspect to it, putting all the pieces together, and then you actually have Felix going out there and doing it. And doing something that no one's ever actually done before, because he didn't have a drogue, he was just actually free-falling. So, he set an incredible mark, and something that is probably never going to be completed, or never be tested. Except, well, we got this guy 2 years later. Look at him. He's a senior VP of Google, and he decides, you know what, I'm going to jump from 136,000 feet. Yeah, he did it. And sure, you didn't really hear about it because it didn't have the branding and the promotional work of Red Bull behind it, but this is kind of what I love about this sport and the whole idea of just in general, with human nature, someone sets a mark, and someone's like, I can do better, I can go further, I can push further. And that's just wonderful. I love that. The end. I'm guessing give this to you.
Thank you. Although I'm just about to give it right back to you. So we have time for a few questions for Graeme. So if you have anything about the talk, he'll actually be back up later for general questions as well. So.
All right. Shania.
Did he experience the violent free-fall spinning during his touchdowns or no? Was he
No, because he didn't get nearly that fast. And he was up much higher, so sorry, yes, go. Oh, sorry. Shania asked if in his test jumps he ever had those spinning issues. And no, he didn't, because he wasn't up as high, he wasn't going as fast, so it was very easy. You notice that when he came out of the spin, he was at 60,000 feet. His first test jump was only from 70,000. His second one was from 90,000. So by the time he would get into a position where something like that would happen, he already had enough air to stabilize himself. So he didn't have that violent spinning issue.
Is there a limit to how high they could go with the balloon?
I guess it all depends on, oh, sorry, my bad. Is there a limit to how high they can go in a balloon? You would just have to build a big balloon. And it would just have to be a question of scale and how much helium you're willing to waste on this. In the back.
Was that a sound barrier, a local sound barrier?
That was that was the sound barrier at sea level because he hit Mach 1.25 with his top speed, and we generally refer to that as the sound barrier. And Mach 1 would be the sound barrier at sea level. Sorry? Yes?
Did he have some kind of instrument to tell him his altitude as he was going down, or did he have to see?
Oh, he had quite a few actually. So in a normal skydive, most people actually have two altimeters, usually an analog or digital one on their arm that they can read the altitude at, and then they'll have an audible that's in their ear that will beep at certain altitudes. So he knew that, especially when he got lower to deploy his parachute, he knew where he would roughly be at. And you never want to really actually go by your judgment on this, because in one of his test jumps, he felt like he'd been falling for a while and wanted to pull, but he was still at 55,000 feet. And he was also on, when he got his radio fixed, he was also in radio with ground control, and they were telling him how high he was and how fast, how far he'd been falling.
What would normally cause the spinning?
Okay, so what would normally cause the spinning?
I got it.
So that was very likely caused by a slight asymmetry in his body position as he was falling, and then it would just build up and build up and build up. And then he wouldn't really be able to correct it because there's very little air up there until he got lower. So that's why they had the safety redundancy of a drogue parachute that he could deploy if he felt he needed it, and I think would actually have also deployed if he had lost consciousness.
Graeme,
Yes, Juhan?
any other nations apart from the US and the Soviet Union have tried this?
Well, in terms of government programs?
Either.
Sorry, so is there any other nations other than the US and the Soviet Union that have done this? As far as I know, it was only those two who have done it in terms of government programs and government testing. There's always been a few private people who have wanted to try to do this. So, for example, this Red Bull Stratos endeavor, that was an international team, but Felix Baumgartner is Austrian. There's been a few Italians who have done, I forget their names at the moment, who have done high altitude balloon rides, but not the jump itself. So in terms of a government program, I believe only the United States and the Soviet Union. I don't, sorry, how many RPMs did he actually get to in that spinning motion? I don't actually know. But he did not lose consciousness, so it was under 120. The Russian guy, Evgeny Andreev? Well, he's dead. He died in 2000. No, he did survive his jump. His compatriot died, though. Yeah, he did a jump from, the Russian and Evgeny Andreev did a jump from 90,000 feet, which was technically the record because the U.S. Air Force never officially released the data for Joe Kittinger's jump. So even though everyone knew that that was the mark to beat, it wasn't the official record. Sorry, what happened to one other guy? Oh, he had a failure in his pressure suit and he died from exposure. The Red Bull guy? Did the Red Bull guy survive? Oh, the Google guy. Oh, yes, the Google guy definitely survived. He's done a few TED Talks on the whole endeavor. Wait, one more question. Oh, pizza slice. I'm sorry, I didn't quite catch the question. Yeah. For the high altitude ballooning, so was that? Was the high altitude ballooning affiliated with NASA? So you're referring to Project Excelsior? No, that was the U.S. Air Force. Because they wanted, the whole point for them wasn't just to see, how high up we can go. They actually wanted to see, can we get people down from this altitude? So, again, as I said, that was spurred from them having a whole bunch of dummies that would have died, and then they realized, yes, we need to be able to get air crews down in case they eject from a very high altitude. So yeah, it was an Air Force program.
So my task is to take you to the zoo of weird and exotic binary stars. This is a special zoo which contains binary stars made up of, that is systems made of two stars, including things like red giants, red dwarfs, white dwarfs, giant blue stars, all kinds of sizes, and I will say a bit more about that. But they come in pairs, and the fact that they come in pairs makes them extremely interesting, makes them have a life that is very different from the life they would lead if they were born and lived out their life in solitude. So, without much further ado, let's go into the zoo. But please do not come too close to the cages. They can be dangerous, and under no circumstances you should feed them. All right, so a slide that is a primer on stellar evolution. I need this so that you can all appreciate that stars are born out of gas in the interstellar medium, and then when they contract sufficiently and get hot enough, nuclear reactions start in the cores of those stars, and they will burn fused hydrogen to helium, and that is the longest phase of the life of a star. When the fuel is exhausted, that is when they're done burning all the hydrogen to helium in the central regions of the star, then the star undergoes a very dramatic expansion that takes them to a stage of a red giant, or in the case of stars that are more massive than the Sun, to a red supergiant. Now, some of you may remember, I don't know, Kelsey is still here somewhere, some months ago told you about the size of the Sun, that the Sun is 100 times the size of the Earth, and that the distance between the Earth and us is like 100 times the diameter of the Sun. So space is basically very, very empty. In fact, it's more empty than the best vacuum that we can generate in the best laboratories and physics labs in the world. So a star on its own, say the Sun, will live out its life starting like a cloud that contracts and starts burning hydrogen, then it becomes a red giant. In the process of becoming a red giant, it swallows Mercury, Venus, and maybe even us, and then ends up its life as a white dwarf, a relatively small ember of a star the size of the Earth. So 100 times smaller than it is today. Well, that's pretty boring stuff, except that for us, it will not be boring when the Earth comes, when the Sun comes very close to us and may swallow us. We may have to figure something out, what to do in 5 billion years or so. Other stars follow lives that are similar in many respects to the Sun, but they go through different stages, different in details, more dramatic perhaps. Some of them end their lives in big supernova explosions, and at the end, what is left over, the ember of such death of a star, is either a neutron star or a black hole. The sun and most of the other lower mass stars will end up their lives as white dwarfs. So in this zoo, we're going to encounter combinations, pairs of these stars that you can pick more or less at random and pair them up. Not all those pairings are possible, but most of them are. And see what happens when you have them paired together. To understand what's going to happen when you have two stars close enough to interact, I have to take you to a little trip on somewhat of a theoretical issue that was first addressed by Edouard Rouge, a French mathematician and astronomer, who was puzzled about the distances of the rings of Saturn and how they could have formed. And he came up with a picture such as this, which shows essentially the way that material would flow if you were to put it in between or around the two stars that form the stellar system, the binary. And it's a pictorial way of describing what happens. It's kind of like a hill, a hill where the material, you can imagine putting something here and it will either roll down into this big pit or the pit next to it. Those are the areas, the volumes, if you like, occupied by the two stars. Now, this is a rotating system. The binary has to revolve in an orbital period to avoid being attracted in and colliding with each other. And so it's a system with rotation, and much like trying to walk in a merry-go-round, you are going to feel other forces due to rotation, just not pure gravity. So if you combine gravity and rotation, that is the situation. One star, the smaller of the two, say, sits somewhere deep in this pit. The other one, the more massive star, in this case, sits in the bottom of this pit. And this hill sloping down pictorially indicates the effects of rotation. So if I put material somewhere out here, where my pointer is pointing, it would simply roll downhill as a result of the centrifugal forces. If I put it, however, somewhere on this side of the hill, it will fall into this pit, into the more massive star. And similarly here, it will fall in. Now, initially, the stars may be deep down inside these pits, but when they go through this red giant or red supergiant phase, they will fill these pits. And if they get big enough, material may overflow this little neck or spout and fall onto the other star. And in particular, things get very interesting when one of the stars is one of these dead embers, a white dwarf, a neutron star, or a black hole. But also it may be possible that both stars are relatively normal and they have grown to a stage where they're big enough so that they can touch, or as a result of the evolution of the binary as a rotating system, it has come together, closer together, perhaps because as a result of gravitational waves emitted or some other mechanisms that I won't go into right now. So if I slice through this to right at the level of this saddle point right here, I get a kind of two special surfaces that have the form of an 8. So that is where the more massive of the star sits, and that's where the less massive of the star sits. And they can, either one of them or both of them, fill these lobes, which are known as Rouge lobes because Rouge was the one who came up with this picture. If, however, you the material somehow ventures outside this particular figure of 8, that is, the only two here that figures that are closed are the one that goes through L1, this middle point, or this. So if material flows over here, it's just leaked out of the system and it will leave. So let's see what combinations we can find in our zoo. In most cases, maybe one of the stars will fill its Rouge lobe, and that's the one then that acquires the spear shape, the shape of this Rouge lobe. And then as it gets big enough, material flows over, forms a stream, and that stream then tries to move and fall onto the star, the companion star, but it can't do so directly because you are in a rotating system, and just as if you try walking in a merry-go-round, you will feel a force pulling you sideways, and that is why the stream, instead of going straight to the other star, goes at an angle and then forms a disk, and material then more or less slowly spirals down on that disk, and in doing so, it will get hot, and that hot stuff will emit radiation, which we can observe. So many systems, the very common systems, are cataclysmic variables or X-ray binaries, essentially depending on what kind of object you put in here. A white dwarf will give you a cataclysmic variable. If I put a neutron star or a black hole, you will have an X-ray binary of one kind or another. Now, there are some systems where both of the stars fill their Rouge lobe and they touch. They are so close that the atmospheres of the stars touch, and you have a common envelope, and you have what is known as a contact binary, or some people call them over-contact binary. In that class, there are some exciting systems. This one here is an example, a relatively common contact binary formed by stars, much the same as the Sun, except that they will touch, and material and energy can flow between the two stars. And that is probably why the temperature of the two stars appears to be the same, although the masses of the stars and the sizes are very different. In the Large Magellanic Cloud, which is a satellite of our own Milky Way, a little galaxy that is our companion as a galaxy, the Milky Way companion, there is an extraordinary contact binary known as VFTS 352. Many of these stars have names that derive from the catalogue of observations that first discovered them. In this case, the two stars are each one about 30 times the mass of the Sun. And they are so massive that they will burn hydrogen so quickly they only last for about 1 million years, which in stellar times is a very short time. So this is the most massive and the youngest contact binary that astronomers know of, one of the sort of prized possessions of our zoo. Some of the more common members of this zoo are the so-called cataclysmic variables that are so-called because they go bump in the night, they have luminous outbursts, and some of them have been seen to undergo an explosion, a so-called nova explosion, during which their brightness increases by factors of hundreds. And they consist of a relatively normal star. By this I mean a live star, a star that is still active, burning hydrogen or some other fuel somewhere and generating its own energy. And then material flows over to a companion white dwarf. Imagine there an object of the size of the Earth, roughly, but with a mass of maybe 60% of the mass of the current Sun. The material then spirals in this relatively thin disk in a vertical sense. So this looks, if you like a CD, perhaps not quite as thin. And in the center, it gets hotter and hotter as the material approaches the black hole, and finally it gets incorporated into the, I'm sorry, not the black hole, the white dwarf. And the temperature, the color is supposed to indicate that it is kind of cooler at the edges and gets hotter as you go in. Some of the more interesting cases occur when the white dwarf, that is at this deep in the potential well and accreting material from the normal star, when that star has a strong magnetic field, and by strong I mean sometimes stronger, certainly stronger than many of the most intense magnetic fields that we can generate in physics labs today. Then the magnetic field is strong enough to disrupt the disk. So there may be an accretion disk outside, but as the material approaches, tries to get onto the white dwarf, eventually the magnetic field wins and guides the material onto the poles of the magnet that the white dwarf, magnetic white dwarf is. Here is another view of one of these white dwarfs with magnetic white dwarfs accreting from a normal companion. And sometimes the material then has to leave the plane of the disk and be accreted on one magnetic pole or the other. Now, you may have noticed that all of the pictures that I'm showing you are not real observations. They are actually artists' impressions based on the science. So there are lots of observations behind this and a lot of theory, but we are never close enough to have the resolution to view systems like this. Maybe one day we will. So in some cases, the central magnet is so strong that it prevents completely the disk from forming, and the material is directly grabbed from the stream and is then guided by the magnetic field into one pole or the other of this giant magnet that the white dwarf is. Those are known as polar or A.m. Hercules stars. Now, when this material lands on the white dwarf, it is essentially in free fall. It is falling from much higher altitudes and much stronger gravitational fields than what we just heard from Graeme. And so they certainly are very highly supersonic. And before they as they hit the surface of this white dwarf, the material goes through a very strong shock. It gets heated up to temperatures of 100 million degrees, and it emits strongly in X-rays. And you may have heard some of that a month ago when Rob Hines, who's somewhere in the audience here, talked to you about X-ray bands. Some of the more exotic objects in this zoo are the ones that contain the most compact of dead embers of stars, and those are binaries that contain one black hole or a neutron star. Very compact objects, so the material, when it flows in, following the accretion, spiraling in the accretion disk, it gets so hot that at times a corona, like the sun has a corona, a low density, very high temperature gas also emits X-rays, is formed around the accretion disk. In this particular case, we have a central black hole in the disk, and as the material in the disk spirals in, magnetic fields in some circumstances are twisted and amplified, and that helps to launch these jets in opposite directions perpendicular to the plane of the disk. In some of the binaries that we know of, these jets reach 90% of the speed of light. And when we view the radiation coming from these jets, from our point of view, sometimes the blobs in the jets appear to be moving apart from one another at superluminal speeds. You may have heard of that concept somewhere in the press. They're suggesting that the material is moving faster than the speed of light, but it is just an illusion. The material is actually moving slightly below the speed of light. One final and very exotic system is SS433. Again, the object number 433 in this particular catalog of strange objects with funny emission lines. And this has now been found. There's still a dispute as to whether the central object here in the disk is a neutron star or a black hole, although I think that the latest results favor the black hole interpretation. And so again, we have jets on opposite directions, this time with about 27% of the speed of light flowing out. But what is unusual is that the disk itself here is wobbling. And as a result of that wobble, the jets are also executing a conical motion. Both the jets in one direction and the other do that, and then generate in the course of time this kind of corkscrew pictures, and we have actual observations that confirm this kind of shape of the corkscrew produced by the precessing jets of these binaries. So let me just say that there are many more of these types of binaries, and I only have shown you some of our price exhibits, if you like. But the time is getting late, and I think we need to go home now. Thank you. So if you have any questions about any of these objects, these systems, or any others, I'll be happy to try and answer. Yes?
On the complex binaries, you said that the temperature of them seems to be the same. Does that affect the lifetime? Either of the stars in contact?
Good question. So the question was, does the fact that they have the same temperature affect their lifetime? It certainly does. The evolution of the two components is different, very different from the two stars if you were to separate, because through that neck they are exchanging mass and energy. And it is this transport of mass and energy that allows the common envelope to maintain the same temperature. And we see that in the depths of the eclipses of these systems. Now, we have known about systems like this for well over 75 years, and there are still questions as to the details of how they really work and how they survive for a long time. Yeah. Over there? Other what? Fusion? No, most of the fusion only occurs in the very central parts of the two stars. And the puzzle with contact binaries is that if you have one star smaller than the other one, the smaller star will be generating much less luminosity by nuclear reactions than the bigger star. And so it should look different in temperature, and they don't. And it is because of this common envelope that keeps exchanging energy and allowing them to reach the same temperature. But there are no nuclear reactions in that neck. The reactions still are confined to the cores. for the stars. Okay, thanks. A couple of questions there. How do we observe that? So the question is, how do we know they are compact binaries? We know that from the observation of the light curves. That is, we see those stars at many random, different cases offer different orientations with respect to us. And we observe how the light pairs. Now you have two pear-shaped objects, and as they rotate in their orbit, we see them eclipsing one another. Now, in most other eclipsing binaries, there are periods where the light, you see both stars, and nothing happens until the two eclipse. One of them eclipses the other, and then you see an eclipse. In these systems, what is characteristic is that the light is constantly varying in a smooth fashion. You had also a question? Where do the magnetic white dwarfs come from? All right, that is in itself a question that is still open to debate. I mean, it is certainly true. The following statement I'm about to make is true naively. If you were to take the sun as it is today and contract it to a white dwarf size, conserving rotation and magnetic field, you would get very high magnetic fields. But it is very likely that there are relic, magnetic fields that are due to a previous phase in the core, and it might require the alignment of the carbon and oxygen atoms in the core in some way that I don't know how to give you a satisfactory answer. But they come from the evolution of stars like the sun. Some of them have magnetic fields. We know that anything that has less than maybe 100 times or 1,000 times the magnetic field of the Earth, we can't detect the effects of those magnetic fields unless we're lucky to see a line that is split by the Zeeman effect. And that, in general, is not easy in these systems. But those very intense magnetic fields, we certainly see the intensity, we see the resonances in the cyclotron line, certain other spectral features that allow us to measure the magnetic field intensity.
All right, so since I have MC privileges, I get to ask the first question, and I'm going to ask everybody something. This may affect some of you, and this may affect none of you, but what do you think about Hubble breaking?
Okay. Hi, I'm a nuclear physicist, and I have no answer to this question other than I'm sad because it takes really nice pictures. I didn't know that had happened, but that's really depressing. Okay, today just keeps getting worse.
Stuff breaks. It's sad. Hopefully it'll get fixed. I mean, it's had a good run.
Listen, we all break down.
Everyone dies.
If you reckon that's the average age for your bracket,
Well, the telescope is mostly in good condition, but one of the gyros broke, and so they can't really point it in a certain direction and hold it pointed so they can do science observations. So I doubt very much that they're going to find a software solution for this, but you never know. These NASA engineers sometimes come up with solutions unexpected. But of course you can't go and service the thing. Oh yeah, you could. Yes.
Can you explain what's broken about the star?
What is what?
Can you explain what's broken to Hubble?
I thought I said a gyroscope. So a gyroscope, well, it's like a spinning top at a very high speed that will keep its direction in space. And those gyros, the Hubble has, I don't know, originally had like 4 or 5, I can't remember. 6. So, but you need, I mean, you can do some things even with 1 or 2, but I think this one was the last one, or maybe there is only, how many are left?
I think it's 2.
2 left.
2.
So they may be able to do certain things, but not keep it pointed in a fixed direction. They may, however, come up with some series of observations that just are limited to a certain portion of the sky, like they did with Kepler. Correct? Observers there. They might be able to find a Kepler 2-like solution.
I don't think that will work with Hubble.
Yeah.
They can do something. They can keep it going.
Right.
Alright.
Yeah.
For the rightmost Alex. Yeah. It's killing me. And it's the end of the night. What is your costume?
Okay, so what's this part?
Start.
Okay, what's this part about? What am I wearing?
Top of the swimsuit.
Okay, where do you wear a swimsuit?
The beach.
Okay, Hawaii, the beach, other places you might wear a swimsuit? A pool!
Pool.
A pool. Shark, yes. Also, I play billiards. Listen, I thought this was going to be a very easy pun. No one got it. I got baby shark, I got left shark, I got the guy from Moana when he changes halfway. Nobody gets pool shark. I got a dolphin. Juhan thought I was a dolphin. Someone thought I was a space horse. And he was sober. Okay, other questions? Science questions, life questions. We have people in all parts of the process of becoming scientists here. Yeah.
Yeah, can you comment on the news about the moon, like exomoon?
Oh my god, okay, wait. Somebody else needs to comment first because I remember seeing a thing and I don't remember any of the details. So somebody else has to talk first so I know what's actually happening.
Remember to repeat the question.
There's an exomoon.
Yeah, the question is about an exomoon, which is a moon around an exoplanet, a planet outside the solar system. And now scientists claim that they have found. I don't know much more about it. A candidate, okay. A candidate is worse than a moon. Do you want to add something there, David?
Huh? Yeah, I just want to say how cool
It's good news.
Like, yeah, it's really awesome. This moon is like the size of Neptune.
Oh, that's the one thing that I was supposed to remember, right? I don't know what that does. Does that mean it's gassy?
The microphone, it's a planet the size of and the moon is the size of Neptune. It's huge.
Okay, wait. So in case anyone didn't hear it, that exomoon candidate is the size of Neptune, and it's used. And my question for you is: does that mean that it's gassy? Is it a gassy thing then? Like, can you be as big as Neptune and be a rock?
I don't think so.
Right. So that's okay. Well, that's interesting, right? Okay. Well, can you be a? But that's still what I'm familiar with rocky moons.
So it's really cool because so when you have a moon, you can measure a mass. Instead, you can get not just the radius, which also like mass density,
Okay.
which then you can tell whether or not it's gaseous or rocket.
Okay, I'm gonna repeat all that because Tabby should be up here on the microphone. But if you have a moon, then you can get a mass. If you get a mass, you can get a density. And if you can get a density, you can tell if the planet is made of rocky things or made of gassy things. Which is cool. That's a cool thing. Oh, we have a question. Yeah. Okay, I'll go first.
Repeat the question.
Okay, the question is, for a prospective science enthusiast, what was your favorite subject as a child growing up in school? And I was one of those kids that liked like every class. I was a total nerd. I really liked art classes a lot. I took a lot of art classes. I took a lot of science classes. And I took like every class I could. I took math and science and art, and history was my least favorite, I will say, which I regret now. So.
I'm kind of in the same boat as the other Allie. I kind of liked a little bit of everything. Besides science, I'd say probably history was my favorite, actually. And then I did a lot of band stuff in school, too. That was good.
I would have to say that my favorite subject going all the way through school from kindergarten up to high school was definitely math, because it made sense to me. I also did band as well, which was very, you need to do a lot of things, but I also played with a lot of Lego, which I think also helped.
What class is that?
It was a class at my own house. After hours.
I grew up in Argentina, and before I knew any English, I certainly could not read English. I was looking at the pictures of some US Army books of physics. And the pictures intrigued me, and that's how I started being interested, first in physics, then later in chemistry. And also growing up in Argentina, I had access to the best skies in the entire world, the brightest stars, and the center of the galaxy. And the Milky Way are so prominent, it's very hard to miss them. And I developed an interest in astronomy, and that just happened.
I will say one thing is that I think a lot of people picture scientists as people who were, all our answers are contrary to this idea, but scientists are people who are interested in strictly science from childhood up, and that is not the route that most scientists I've met have taken. For myself, in high school, I took a lot of art classes. I almost applied to art school. I actually did apply to college as an English major. I switched subjects to math and physics. I took a year off after high school and played in a band for a year. And then I took a year after undergrad and went to band for a year. Went to play in a band for a year, and then went to graduate school. So your path does not have to be like physics the whole way, or astronomy the whole way. You can have other interests, and they're totally not going to hold you back. In fact, they'll help you a lot. Okay.
All paths lead to science, remember?
Okay. I had a chemistry teacher in high school who used to start every class describing how literally every other class you ever took in high school or college or anything led back to chemistry. Everything you learned. If you learned French, it was so that you could understand some of the chemical names of chemicals and things like this. He was brilliant. Anyway.
What is your favorite Halloween costume you've ever worn? All of you. There we go. You've ever worn.
Start on that. I keep talking.
Okay. Pac-Man.
Oh.
Yeah, let's go. It was either Mario or Pac-Man, but let's go with Pac-Man.
Right. But like yellow or a huge sphere around it?
Huge cylinder around me with the wedge cut out.
It was really hard going to a house party wearing that thing, but I made it work.
I was a Dalmatian, and my girlfriend was Cruella de Vil.
One time I was little Bo Peep and my nephews were the sheep, and it was fun because my sister and I handmade all the costumes.
I think when I was a kid, I insisted one year that I be a fawn. So like one of those like goat people that stands on their back legs, right? And my mother made the costume and it looked absolutely ridiculous. I was wearing like big puffy like woolen shorts. It's great. Still the best costume. My mother handmade all the costumes though. You don't thought my best costume was today's. Yeah.
So go back to the round minutes. What is it that causes somebody to die?
Well, okay, so what causes someone to die when they're spinning too fast? It's, really it's just too much blood into the brain. And you're looking at a cerebral hemorrhage. Yeah. Well, I mean, if you're spinning around and your head's at one of the axes, it's all going to spin it that way. But yeah, so you'll lose consciousness, and then that'll be the story. On that note,
Another question.
please don't end on a morbid note.
I have a question.
Hey!
What is your favorite color? If someone doesn't do the Monty Python bit, I'm out.
Blue. No, wait. What?
Is that joke right? Nobody's getting my jokes tonight. This is terrible.
Yeah, I'd say probably blue.
I don't have a favorite color. Green.
Pick one.
Brown. I like brown.
Be decisive.
I like brown. I'm also on team blue.
Green, I'm sorry.
No green.
You've made an enemy tonight, you. Would that be it, or is there any other questions?
Do you guys have any questions? No?
You always have questions. Seriously?
You're running out of the building.
Hey, for your careers or beginning of careers, any scientists that inspired you particularly?
Sorry, Tabby.
Sorry.
So the question is there any scientists that have inspired you particularly? I'm going to think about this one for a second and take the coward's way out and pass it to Juhan.
Well, it was Martin Rees, my thesis advisor. And I still admire him as a very multifaceted person. Later on, I got to know Steve Hawking too, but he ran over my feet.
My high school physics teacher, Susan Romano, is the reason why I went into physics, so I would say she's one of the more inspiring scientists in my life, although I think she would refer to herself as an educator rather than a scientist. The I don't know, grand matriarch of my field, Maria Gobertmeyer, is a really inspiring figure. She's one of 3 women to ever win the Nobel Prize in physics, and she won the prize for her work on the nuclear shell model, which is what I also work with. So, very inspiring. Okay, we're not ready yet. Vamp.
Okay, well, I'm going to limit this to like a scientist that I've actually worked with, and I hope he never sees this because he has a huge ego. I mean, for lack of a better term, he is a bit of an ass. And I've called him that to his face. His name is Guy Savard, and he's the science director at Argonne National Lab, and I've worked with him quite a bit, and he, again, while also being a bit of an ass, he really illustrated the importance of getting things done, being direct, and also something that I found very refreshing was that he wasn't really pretentious. So when he was introduced to a student, no matter whether it was an undergrad, graduate, or if it was a postdoc, whatever, he introduced himself as Guy. So you didn't have to worry about, oh, am I addressing him by professor or doctor or director or whatever. He was just very much no nonsense. We're here to do the science, and when we took lunch breaks outside the lab, when we were at a place that served alcohol, as he said, we're not flying airplanes, yes? We're just running an accelerator. But what do you expect a French Canadian to say?
Okay, so you asked me that question, and I suddenly forgot every scientist I've ever known. But kind of inspiring in kind of a negative way, I guess, is my high school physics teacher told me that girls couldn't do physics and I should apply for something else. So that's been inspiring in a spiteful way.
That's not true. What? Step up and you die? Yeah. I mean, we're here. We're Team Alley.
Hey, Team Alley.
Okay.
Oh, wait, you got it wrong. What is the highest jump all of you have ever made? Who's got the record?
That's it. Okay, that was my answer.
No, all of you.
Okay, I've never had to jump with oxygen, so 14,000 feet. Yeah, it's fun. I think the funnest part is, sure, you can be with a group of people and do, we're going to try to do all these formations or whatnot, but the best part is when we do what we call a zoo dive, where we do something silly, whether it's jump with an inflatable dinghy and try to ride that down. What else? Try to dive through hula hoops, zoom around a bunch of inflatable pillars, try to assemble a Mr. Potato Head. It comes out a total mess. But I think my absolute favorite, all right, so Rob, as a Rob and an Englishman, you'll like this. Every Summerfest, which is it's a boogie, which is a skydiving festival that's hosted by Skydive Chicago. It's one of the biggest in the world. And every year there's this guy that comes in from England. His name is Rob. And he decides to organize what he calls a no jumpsuit BFR. Now, a jumpsuit helps you a lot when you are trying to fly and be very precise in your movements. And a BFR stands for big, friendly, or fuzzy round, as in we're trying to make a big circle. So you have this huge mass of people that try to pile out of the plane all at once, and you have this just complete mess in the air, and you're trying to build a circle out of this. And if it forms, he buys beer for everyone on the drop zone. And that would be like 300, 400 people. He's never had to do that because it's never formed. He takes people that have every single level of skill, from just babies that have 50 jumps to sky gods that have 6,000. And every time he tries to announce it, he ends every statement with "God save the Queen," and there's a little bit of a pump-up speech in the plane. But yeah, he's never, ever, ever had to buy beer, because it's never formed, and it's a total circus, and it's so fun.
jumped off.
Yeah, I did 14,000.
I jumped off a pretty big rock once. That was like 4 feet.
Yeah, I like jumped off a. I mean, maybe it was like from the railing down into a pool of water. This is much like.
Yes, well, similar. Maybe jumping into water, yes, and that is the deliberate jumps. But, deliberate jumps when I willingly jump. But I did have once an accident in Sussex. Was working on my first postdoc, and I was running down the stairs trying to catch a train, and I stumbled. And I was going to die. I thought I'm dead. But somehow instinctively I bent down, and I took a complete turn, and I landed on my feet. It was a stunt, but accidental one. But I paid a price for it because since then I've had some back problems.